Hello my dear students, in the previous class we discussed about magnetic dipole moment when the electron is revolving in orbit. Today's class is very interesting. We are going to study about moving galvanometer. See, whatever you are seeing in the diagram, so that represents the moving galvanometer which is inside, okay. So this class says about the moving galvanometer which you can see left side the diagram. This is an electrical instrument which measures the small value of the current. Ma'am, so as we all know that ammeter is the measuring of the current. But how this moving coil galvanometer becomes a measuring of the current, that to small value of the current. So this plays something important role, and in today's class let us study about this moving coil galvanometer. So how we can say the moving galvanometer is an ammeter? So it's a very simple one. When I am considering a resistance which is having a small resistance, that small resistance I need to connect with a galvanometer parallelly. So when I connect that small resistance parallelly to your galvanometer, then that will act like a ammeter. So now the galvanometer is acting like a ammeter. Yes, we can see this as ammeter, but when you need to remember that in this only we can consider the small value of the current. So here I cannot consider my desired value of the current. So it depends the combination, okay. So I need to consider a small value of the currents like micro ampere current, so milliampere current. So very small amperes of the current I can consider in this, because here it measures only least one. When I'm expecting like 2 ampere, 1 ampere like that, we cannot measure in this, because see, when you are considering the diagram, so it depends on the rotation, okay, where the upper part where it helps for the rotation based on the torque created, so it will gives you the reading of the current. So the torque will not goes the complete rotation, it takes, so if it goes more rotation, the springs whatever it is connected, it disconnects. Therefore only a small value of the current can be detected or identified in this moving galvanometer. So what will be the principle of moving galvanometer means? So here I am going to consider based on the experiences of the torque, okay. So this torque, how it is created in the previously we came to know, right? So now let us study, we will place in a magnetic field, then we will produce a torque, then how this working is happening in the galvanometers, let us study in the today's class. So I hope so up to here it's clear. Always please make a note that I cannot find the large values like 2 ampere, 3 ampere if that is my desire, but I can identify based on my resistor by doing the parallel combination. I can get my desired value of the current. So by doing the resistor in the parallel combination, I will get my desired value of ammeter, okay. See, now when I am considering this particular diagram, if I know what is resistance and what is current, I can identify the voltmeter. So if I know what is voltmeter and current, I can find the resistance. Where is the resistance? See, here is your resistance. One coil will be there. In that particular coil, if I identify the resistance, if I know the current, then I can identify the voltage also. Then it is acting like voltmeter also? Obviously yes, it is acting like a voltmeter also. So here it will measures very small voltage, okay, it will measure small voltage. So by this it's clear that the moving galvanometer, it is acting like an ammeter also, it is acting like a voltmeter also, but it is measuring very small value of the current and small value of the voltage. So by using the coil resistance, we will identify the current and even the voltage. So from the Ohm's law, that is V is equals to IR relation, we are going to identify this current and the voltage resistance, all this relation we will use and we can identify it. So without wasting our time, let us study the working of the moving galvanometer. Now let us consider this is a magnet and this is a magnet. Okay, these two magnets will gives you the magnetic field like this. Okay, and inside that there is one coil which is placed there. Now let us do with the schematic diagram. See, this is what the coil which has placed. These two are the magnets which you have seen. So here which kind of field it is created? It creates a radial magnetic field. So this radial magnetic field, about this let us study later. So now from the magnet it gives radial magnetic field. So we understood that there is a magnet over here and there is a coil at the center, and we know some wire, let us connect to that. Okay, so for that coil let us connect the wire. When the current carrying coil is placed in a uniform magnetic field, it experiences a torque, then it starts rotate like this, correct? It starts rotate like this. You can see some needle, right? This is what the needle which is connected. It will also start deflecting when it is rotating. See, when it starts rotating, the needle will also move. See, initially in this position it moves here to here. So it moves more, means it will go down, correct? Still it will start deflecting. So based on the rotation, the needle movement you can see there. Is it or not? Now let us consider this in the diagram. See, these two are the magnets which gives the magnetic field. Due to the magnetic field and here the current is passing. So when we place a current carrying conductor in the magnetic field, there will be a torque created in the rectangular coil, which you know that. And this rectangular coil is connected to the insulator, and that insulator which is having a spring which you can see in the diagram. Now as you see, like here I'll connect this to one terminal because I want the current to pass through that, where you can see here in this diagram. Okay, I'll connect some wire to that terminal where the current should pass through that. Okay, and at the another terminal I'll be having, from both of that I will connect to battery. Okay, this is how I will be connecting. You can see left side of the diagram. Okay, now when I connect with the battery, the current will be passing through that. When the current is passing through this particular galvanometer, what it happens? So let us pass the current. So when the current is passing from the two terminals, from positive to negative, the current is passing. See, the current is flowing in this particular direction through your coil, where you can see in the diagram, correct? Positive to negative. Now in the presence of the magnetic field, the current is flowing like this, and due to that there will be a torque will be experienced. So the torque or the force is experienced and it creates a rotatory motion. So in the presence of the magnetic field and the current, it experiences the torque, where you can see with the arrow mark. Okay, when it experiences the torque, where see here it has connected to your spring. Okay, it is connected to the spring here. So when the rotation is happening, your spring also will start moves. See, example, the rotation is happening like this way. This spring will be having a restoring force. You know what is restoring force in your first view. So this restoring force will also give the force. We know that the torque is created there, and here is your spring. From the spring there is a restoring force also created. So let me explain detailedly. So this is what your spring. So this spring, example, the rotatory motion is happening in this way. The string restoring force with the support of rigid support. Okay, the restoring will be opposite direction. Okay, if the rotatory of the torque, okay, the torque is experiencing like this, it gives you the rotatory motion. The spring will gives the another force, that is nothing but a restoring force. Okay, if the see, it is opposite to your rotatory motion, which you can see here. Okay, so the spring is going to give the restoring force when the rotation motion is taken place. Okay. Now let us study detailedly. So if a current is passing, how much will be the deflection, and based on the current, how many number of times the deflection is happening or what is happening, let us study now. So let us study now. See here, same diagram. I'll consider the top view right now. So this is what the top view. Here I'm not considering the bar magnet. Let me know why. And you can see the radial magnetic field in that. And here I can see only the one coil face. That blue ray where you can see the right side. Only one part I can see. So this particular part where it is perpendicular to the surface, which you can see there. So how it is moving, it is going down, right? This particular edge also it is going down, and here right side also it is going down. So by this we can see the down surface like that, and here also, so which is perpendicular to the surface. So let us consider the current I is passing through this. So when the current I is passing through this, what are the things which we have required? We know that when the current is passing in the presence of magnetic field, the torque is created. Okay, before going to the torque, I need to know what is the force which is created between the surfaces. So let us mark. So this is A, and this is B, this is C, and this is D. So let us calculate what are the force which is acting at your A, B, C and C, D everywhere. What are the force which is acting on that? And you remember, if I am considering BC and AD, the whatever the gap here we have, it is negligible. So I can equate this BC and AD. Okay, that gap is negligible. Let us identify like what happens in the AB side and what the current is passing, fine, like what will be the force. So before that, let me consider an axis. Okay, let us consider an axis. Take this as a y axis, and this is x axis, and this is z axis, that is nothing but towards you, which you are seeing the phone you are holding towards you, that is nothing but your z axis. So I will name now, this is y and this is x and this is z, where you can see the rotation will be created in this way, right? But you are observing that your AB is parallel to your y axis, right? See the diagram, AB is parallel to your y axis. When I am seeing from the top view, okay, how will be the magnetic field? So let us write the magnetic field here. See, so from the top view I will be seeing, so how will be the magnetic field? It will be like this, right? It is like this, where you can see in the diagram. And down, okay, down it is like this, right? Like this your magnetic field is distributed. If you want, you can pause it and you can check it out. Okay, see that your magnetic field is covered your z and x plane. Okay, so if you want, you can pause the video and check out, okay, how the magnetic field is covered your x and z plane. Okay, because it is a radial magnetic field. Okay, so now let us write detailedly. Okay, so if it is like confused to you, let me write once again down neatly. So I am writing the coordinates, okay, and here is your, so let me take the coordinate here x, no, this let me take it as z, and here x, and here it is y. So think this is your magnetic field lines I am writing, which is parallel to your x and z plane. Okay, x and z plane, which is parallel. And let me consider this is nothing but your AB and ABCD, both are parallel to your y axis itself. Okay, so this is how my AB element have placed, and the current I is passing through that AB element, or it's a current carrying element, right? So when the current is passing here, and in the presence of the magnetic field, that the torque is created. So the between that rotation is created place between this magnet itself, right? I have written the two position of that AB also, which you can see. There also current is passing, and upper part is also current is passing, where you observe that current flowing and the magnetic field both are perpendicular. I marked in the red one, right? So both are perpendicular to each other. when the angle made between the current element and the magnetic field, current element is nothing but what? IDL into the magnetic field, that is nothing but sine theta becomes 90 degree, sorry, theta becomes 90 degree. So therefore my magnitude of the force will becomes ILB, where theta here it is 90 degree. So sine theta, sine 90 is nothing but 1. Therefore I can write my magnitude of the force is ILB. So you understood. So how I have written the magnetic field, the sine 90 becomes 1. Okay, so this is about the force magnitude here. Do you think that only one rotation is taken place? No, there will be n rotations will be taken place. There will be n number of rotations will be taken place. So I will write here n turns of rotation will be taken place. Suppose like if the coil is AB, it's 1, like I am taking like n number of coil, okay, AB it has more number of turns, so I will write it as more turns over here. So the current passing through that will become not I, it becomes Ni. Then obviously your force also becomes n times of it, right? So you can write Ni here. So let us consider force direction here. See, by using the Fleming's left hand rule, we can identify what is our force direction, right? So consider the magnetic field direction, which is, and current direction. Then what will be your force direction? So your force direction will be in this way, right? So this is red mark we can observe, that is nothing but your force direction. Now here at the AB, this is what my force direction is. We're coming for, same thing will be applied in the CD also, but the direction of the current is different. So the same magnitude will be there. So here the force, whatever it is exerted in the AB, same force is exerted at the CD, because the CD is also parallel to your y-axis. So which is opposite direction, right? Because the current direction differs, the force direction also differs. But here also there is n number of turns, where coming for the CD also it is n number of turns. There will be no difference. If AB is having 2 turns, CD is also having 2 turns, because it's an entire coil. So my force value will not change with my n also, okay? The magnitude remains same. Therefore the magnitude of the CD is also same as your AB. Now I can write it as magnitude of CD is FNILB. So by using the magnitude of the force, let us find the torque. So torque is equals to force into the distance, perpendicular distance. Now what is the perpendicular distance? Where you can see this is a rectangular coil. Same thing we did in the rectangular coil torque experience, right? This we are taking the breadth, okay, BC distance. I will take the perpendicular distance from the force. So this B is different and this B is different, right? This AB, B is that point, okay? Here B is a magnetic field. Now the perpendicular distance between them is small b, that is nothing but a breadth of the rectangular coil. So the distance between them, it is nothing but, so between that torque, that is the force which is acting oppositely, so it is separated by the distance. I will write it as B, okay? So I will write F into B. Now let us substitute. What is the F value? Let us substitute there. So what is my F value? Let me write, okay, that is NILB. First I will write the small b into B, because L into B is the area, okay? So L into B, B. So L into B, in the place of L into B, I will write the area of the rectangle. So this equation will becomes, see, this equation becomes the torque is equals to NIAB. Same thing I got in the torque experience. However, what are the steps you are using? Same steps you are using here, but the principle is different. Okay, and you observe the spring is there. The spring is also opposite. I said whatever the rotation is taking place, the restoring force is opposite to that. Okay, so the restoring torque. See the word you can see here. The C is a constant for the spring, and it is restoring torque per unit twist. So what exactly is this? The restoring torque per unit deflection. Okay, so the per unit deflection, it gives you like this, that is theta into theta into c. So let me write here, I will write the spring here. When I apply some force, it will displace us to x. Okay, so that constant, it is nothing but a spring constant. I will write it as k. X is what? X is nothing but displacement, and k is nothing but spring constant, where F is a restoring force. Okay, this is what, same thing I am writing here in the presence of the torque, and the C is nothing but your restoring torque per unit deflection. Okay, and theta is nothing but deflection of the coil. So this is about the torque. Okay, let us equate this two now. Okay, here torque is equals to theta into c, and I said you what is, why we are taking, how we are taking, F is equals to x into k. Same thing I will be taking for torque here. Now let us consider the case here. The current and the magnetic field both are in the same direction. When the current and your magnetic field both are in the same direction, then the whatever the force which is exerted is zero, because the theta here it is zero. Therefore, the force exerted between them is zero. There should be some angle between them, not a zero. So as I said to you, if the angle between the current and the magnetic field is zero, there is no kind of force. If there is no force, there is no torque created. So what happens in this BCAD, I'm going to explain right now. See, this is what the position of a AB, where it is a parallel. Okay, it was parallel. Okay, now let me think, it has rotated this particular point. Okay, from this point, let us it comes to the another point of that. Okay, it is coming in this way direction. So what happens here? Now the force is created. Fine, now the force is created, but when you come to the BC, the force will be created upwards. When you come for the AD, the force is created downwards with the equal magnitude. Okay, so at the BC and at the AD, whatever the force which is acting, okay, that is both magnitudes are equal and with the opposite direction. So initial stage when I am considering, the angle between them was zero. Later when it moves from here to here, it forms an angle and it creates a force, but whatever the force it's created, it is equal and opposite. Therefore, when you consider at the point BC and when you are considering at AD, both are opposite. See the arrow mark there, it is upwards and this is downwards. So whatever the force which is created there, so that it cancels each other. Okay, then there is no torque effect which is created by this BC and AD. Okay, now by which I am considering the torque? I am considering the torque only from AB and CD. Okay, so this forces get cancels, BC and AD forces get cancels each other. Now I can equate my torque and the spring constant torque. I can equate, I can follow the derivation now. So this is about the BC and AD phase, and we calculated already what is the force at the AB and what is the force at CD. Now let us equate that. That is your torque NIAB is equals to your C into theta. Okay, this theta is nothing but a deflection which is observed. This I need to measure in a radian. So I am going to identify the theta. So one side, yes, it is rigid, but another side you can measure, right? This side it is rigid, but another side I can measure the rotation. So we know that this rotation and the rotation of ABD coil is different, okay, opposite direction, right? So now let us calculate what is the deflection of the coil or a pointer of the coil which is rotating. Okay, so theta is equals to, I am writing theta and you are just writing what is that, that is N I A B divided by C. Okay, where C is nothing but restoring torque per unit deflection. So this is what I got, and you should remember one thing: the coil rotates until the restoring torque will be equals to the deflecting torque. So when this is happening, the coil will be in the equilibrium position. Okay, so when the coil rotates until the restoring becomes equal to your deflection torque, until that it will be rotating. So this is what the expression for theta. So this is what the expression for the deflection. Okay, this is where we have studied. Please make a note of it and take every running notes. Now let me write the expression. Finally the expression will be like this, that is theta is equals to NIAB divided by C. Now we will study the another important thing, that is nothing but about current sensitivity. Okay, so let us study now about the current sensitivity. What is this current sensitivity? Let me take with some example. Okay, so I will write the galvanometer here. So while I am writing the galvanometer, I'll take two galvanometers. Okay, so let me write here. I'll write the two galvanometers here. I am passing same current. Okay, this is what the deflection. This is a deflection needle. Now I am passing the same current to the both of the galvanometer. So here it shows the deflection like this. Here it shows the deflection like this. By this, what you are understanding? Which is showing more deflection, which is showing less deflection. If it is showing more deflection, means it is more sensitivity, right? It is having more sensitivity. Therefore, how I can say the current sensitivity is nothing but the deflection produced in a galvanometer per unit current. Is it or not? Based on the deflection per current. So by this I can say if there is more deflection, there is more sensitivity in the galvanometer. If there is a less deflection, there is a less sensitivity. So I mentioned that deflection per unit current. So I can consider the current sensitivity as deflection per unit current. So I'll be writing SI as the current sensitivity. So deflection means what? Your theta, right? So in the place of deflection, I'm writing what? Your theta divided by per unit current means your I. Now let me substitute this theta value. So NIAB divided by C, where I and I get cancelled. So I'll be writing NAB divided by C. So this is what my current sensitivity, where if you are observing how does this current sensitivity will depend. First we are coming for the N. In N numbers of turns if it is there, the current sensitivity will be more because it is directly proportional. We are coming for the area. If area is more, again the current sensitivity will be more. We are coming for the B. B is nothing but a magnitude of magnetic field. If magnetic field is more, then the deflection will be more. So it is also directly proportional to magnetic field. Least is nothing but your C. C is inversely proportional. C is nothing but it's a constant which is created in the spring. So the spring which is connected, the rigidity should be more. Means the spring rotation is more, the coil rotation also will be more. When the coil rotation is more, the deflection created in the coil will be more. When deflection is more, obviously your current sensitivity will be more. So C is inversely proportional to your current sensitivity. So this is about the current sensitivity, how it is depending, what are the things which is directly proportional and inversely proportional. Similar to this current sensitivity, now let us study about the voltage sensitivity. Okay, because as I said you, this moving galvanometer will be satisfied for the voltmeter also. It not only acts like ammeter, even voltmeter, right? That we will study at the last part now. Now I will calculate the voltage sensitivity. So voltage sensitivity is also same as your current sensitivity. If deflection is more, so I will write SV, okay? SV is equals to theta by V. If deflection is more, your voltage created there will be more. same thing I'll be writing in the current sensitivity. Okay, deflection per unit voltage is nothing but your voltage sensitivity. Now I know what is theta. Okay, before that we know that V is equals to IR from the Ohm's law, right? So we know that V is equals to IR from the Ohm's law. R is nothing but a resistance of that coil. Okay, now by using this relation, that is R is equals to V by I. Now I will substitute in the place of V I will be substituting, okay, IR. Now theta by I is nothing but, I got here, please check above, that is NAB divided by C. Theta by I already I got it, so I substituted that value. Now you have remaining is R, you just write the R. NAB divided by CR. So this is what the expression for the voltage sensitivity. Again it is directly proportional to what are the things and only inversely proportional to resistance. Now this is about the voltage sensitivity. Now let us study about the galvanometer to voltmeter. I should connect the resistance with the series which is having high resistance. Okay, so let me connect with the high resistance. The galvanometer should be connected to the high resistance. In voltmeter I should connect in series with high resistance. Okay, so the resistance will decide what is the range of the voltmeter. So in which range I want the voltmeter, so it will be depending upon the resistance. In what value of the resistance you take, that value that decides the range of the voltmeter which you want. The galvanometer resistance is equals to G. Let me take G as the galvanometer resistance. Okay, so I will be taking galvanometer resistance as G. The current which is required to full scale deflection, I will take it as IG. So whatever the current I am passing, so that current should be deflected. Due to the current, the galvanometer should be deflected. So that current, let me take it as IG. So the range of the voltmeter which I connected there, so I will take it as V. Okay, so we know from the resistance how it is connected, which is in the series. I will take it as capital R. So these are the things based on the Ohm's law. I can write V is equals to IR. So IG is equals to V by R plus G. R and G are connected. See, I is nothing but what? Current flowing through that. R and G which is connected in series, right? Therefore, when it is series, effective resistance, how I will take? R plus G. G is also a resistance of galvanometer. So when I simplify it, I hope so you can do with the mathematics, okay? When I simplify it, it becomes V by IG minus G. So this is what my expression. So the equation of the resistance which is connected in series of the galvanometer, it becomes, for the voltmeter the resistance should be more. Now galvanometer into an ammeter, how to convert it, let us check. See, when you consider the galvanometer, for the conversion of the ammeter, the current should pass through that, where here I need to consider parallel combination. Okay, I need to consider parallel combination. Here whatever you are seeing, the galvanometer scale is very small. Just imagine if the large number of current is passing through that, they cannot show that much of deflection. Therefore the least or small current can be passed through this galvanometer because it is having the least division. Okay, so if it is as a least division, there will be current passing through that will be very small. So I should consider very small current which is passing through it. So here is my job to make the current flowing through the galvanometer should become less. So what I will do, I will take one resistor which is having parallel combination with a low resistance. Okay, there is a low resistance value, so it will not resist the current much. Okay, so when the current is passing through that, what happens, the large number of current when it is coming from here, it flows through the low resistance. Least number of current will be passing through the galvanometer. Least will go in the galvanometer, large of the current will be passed through this resistor which is connected parallelly. Okay, so only we have took low resistance. Okay, so this low resistance can be set as a shunt resistance also. Okay, now the current is passing where the current maximum it is passing through your shunt resistance itself, the minimum current which is passing through the Ig. So the current gets splits into Ig and remaining is I minus Ig. So whatever the current it is passing in the Ig, this is the maximum current for that galvanometer. So it shows the full deflection. See, maximum current here, what I mean to say, example 0.1 ampere is less for U compared to the I, but that 0.1 is more for that galvanometer. Okay, so if the 2 ampere current it is passing, 0.1 current will pass through this. Okay, that resistance which is there in the galvanometer is nothing but galvanometer resistance G. Next, shunt resistance is symbolized by S. Okay, so leaving current will be, again it is I, because it is connected parallelly. Okay, now, so what are the current it is passing through the shunt resistance means Is is equals to I minus Ig, that is 2 ampere current minus 0.1 gives you the remaining current, is it or not, that is 1.9. This is what the current which is passing through the shunt resistance. Since this galvanometer and the shunt resistance connected parallelly, their potential is common. Correct? No, in the parallel combination, the potential difference is common. By Ohm's law, I know that V is equals to IR. So I, in the place of I am writing Ig for the galvanometer. Resistance is G is equals to, in the place of resistance S, what is the I which is passing? I minus Ig. If I want S will be equals to G into Ig divided by I minus Ig. So this is what the equation I will be getting. The shunt resistance is very small because Ig is only the fraction of the I. But the effective resistance of the ammeter, let me take like this, that is Ra. So here if I am measuring, take that as ammeter Ra. How this both the resistance it is connected? Okay, effective resistance is nothing but ammeter A. Okay, so resistance of the ammeter. Okay, so 1 by Ra is equals to 1 by G plus 1 by S. Since it is connected parallelly, I am using the parallel combination formula. So this I can write it as Ra is equals to Gs divided by G plus S. So this is what my resistance of the ammeter. Okay, that is Ra. I have written in this format, that is Ra is equals to Gs divided by G plus S. So this is about the today's class. So whatever we did, all this are very important. 2 marks question, 3 marks question. Practice well and have a nice day.